Class2. Let's come back to digital logic. So we have second lecture next Monday, and this Friday I'm not going to teach. I'm just going to read it. Okay, you can come with your questions. Please go and review whatever last few weeks are related after first attempt. What the action part, we're going to be part of the exam. So take a look. Any questions you have, anything, you can come up with those questions. And I'm going to review all those parts. I mean, something left.
One, are we having a quiz?
We don't have quiz on Friday. We don't have quiz on Friday. Yes, after midterm 1. Yes, just after midterm 1. But yes, if not, it's just after midterm 1. Yeah. Okay. But today we're just going to talk a little bit. So the stuff related to latch and memory is not going to cover in the exam. So I'm not going to teach too much today about sequential logics, but this part is not covering that exam. Most of the parts is related to time methods. Okay, so last class we explained sequential sequence and it started, and you learned how sequential sequence work. We explained 2 types of sequential sequence. And they have, both of those have memory. To do what? To save the state of the system. Saving the state of the system is how to have better answers for so many applications. You need to keep track of state. And what is a state? A state is information that can summarize system. Information that you can summarize the system with that, whatever system you have. And we explained about that. And we also mentioned when you have memory, sometimes changing those elements of memory at the same time can make some problems. And we call them hazards that coming mostly from race conditions and things. So we're going to see them today more. We explained some methods that we can solve them, especially when you synchronize sequence using clock. That's one of the ways. But some system doesn't need clock because of their characteristic. You want higher speed, for example. You don't need to wait for clock. You want to make, fast decisions. Is any general way to fix it? Yes. Raymond actually. And yes, I checked it out. And yes, there is some ways. However, most of them are not so general, but one of the methods is general, and that's actually using redundant terms to confirm the result. So like what? For example, I'm not going to go detail because it is like advanced digital systems. But I'm just going to tell you how that means. For example, do you remember in Carnot map, when you are make the circuit shorter, like for example, you have this Carnot map, 0, 0, 0, 1, 1, 1, 0. This is A, B, and C here, 0 and 1. For example, you have 2, 1 here, 2, 1 here, 0 here. So we said the best way to group this is good to group these two. And the result, F, will be just B bar. But what about we have a redundant term? Like, for example, these two are also redundant. So you just can consider that too as a confirm, as a redundant term. So this is also equal to B bar plus this two, B bar C. This B bar C is a part that can confirm the result of that. If, for example, however, in this case, it's just B. However, B bar is also maybe, but you get the point. Sometimes adding some extra actually terms can help for solving the race condition. However, we have different type of, race condition and hazard, but this is one of the way, is mostly general way. But the best way is to use clock, make the system synchronous. Today we're going to see other methods too, like for example, put control to not let the system decide by itself. We give some specific time and be control, or not be, I mean the control, the system control, the circuit control. That's also possible. But today we want to, so that was from last class. We want to talk about memory elements today. And we want to start how we created memory and how we give control to the memory. So the first memory, it was so simple. So anytime, if you have a loop, so if you make a loop, for example, with an inverter, you just make a loop. So the loop in the system means passing electron. If it's 1, this 1's gonna repeat. This is just memory. It's just gonna repeat forever. Obviously not, because you have some, things that makes this 1 less. That's why we need refreshing. Anyway, this is a simple way to make memory. But look at this. This is 1 coming here, gonna get 0, and again 1, 0, 1, and it's it's gonna be a That's why if you put 2, for example, not, it's gonna be more stable, because if there is 1 here, 1 gonna stay. This is the simplest way to make actually memory. So normally making loop in the system makes memory. We're going to talk about that, and then the type of memory that doesn't need clock, at least edge of the clock, or latch. We're going to go for that. But next week we're going to talk about other type of memories with edge, because to solve the problem of race condition and hazards, we need to get triggered by edge. That's the best solution for avoiding these problems, race condition or glitches and hazard. Okay, so let's see what we can, how we can make memory. If you look at the DNA, but DNA is some molecules and make a structure like that. So, but what is the characteristic of DNA? Is actually memory. Is a huge memory. Why is memory? Because of these loops. And these loops are actually making this memory. This memory, after evolving, created and adjusted and weighted, and this is something that I'm not sure, but probably this came to the mind of the people and said, oh my God, we have this in nature, why we don't have it in, for example, computer or digital systems? So we can make, because whatever happening in DNA, those loops, those molecules, we also can have something in diode or transistors, and we can make something, we can simulate this, we can get idea. So they made loop. The first loop that they came to, anyway, that's called feedback loop. They use feedback loop to actually keep the electrons stay in the same level, you know, or voltage stay in the same level, the passing electron. And that was the first first things that came to my mind. But they said, okay, let's make the smallest or easiest loop with two inverter. Is gonna be stable. If it's one, it's gonna stay one, and if it's zero, gonna stay zero, because one gonna negate the effect of the other one. So this was the first idea that came to the mind to make memory. Two inverter. If Q is one, you're gonna get zero and again one, and Q is always one. It's gonna stay one. And if it's zero, you're gonna be zero, you're gonna get one, and again zero, and zero gonna stay forever too. But this was the first actually try to make memory. It works, but the point is there's no control in that. How we can put something inside, how we can control it. They said instead of having, for example, inverter, what about we use, for example, NOR or NAND? Because NOR and NAND, if you know, if you remember, if you connect the input together, they act as an inverter. This is same as just inverter. So we can do that. And for this is for NOR, we can use NAND as well. This was the basic of like a history behind memory in a nutshell. So this was the one that I already explained, and this is a cube. This is one inverter changing to zero and repeat. So what is latch? Latch is actually changing these two inverters with NAND and NOR. But as I explained, so how they did that, I said, okay, so this is two inverters that looping. And imagine I put NOR instead of that. One NOR here, another NOR here. Okay, so this is same because NOR with connecting inputs act as an inverter. But what about we give some control to this? We take this input and this input to something else, like for example, this is set S and R, and this be Q, for example, this be Q, oh, this is Q and this is Q bar, for example, because these two are negative of each other all the time. So right now, with this system, we have two control inputs. These control inputs actually kind of define what is Q and Q bar. Still, we have memory. So this is called latch. So latch is adding some control input to that simple 2 inverter, but still there is no clock, but it's kind of level control. When I'm talking about clock, an age control is the main part of clock, okay? So why age? Because is decision supposed to be so fast because of all of those problems that happen in race condition? It is just edge. The possibility of having race condition in that time is very low. But if it's level, if you want to make decision in a level, like you have level in this level, that's enable. Like enable signal is into time. In this time, you can have other race problems. Okay, so anyway, we're going to talk about this soon. Yes. So this was the first latch. So and then if you wrap it up, it's going to be like that. Bring this part up. It's going to be Q. It's going to be Q bar. It's going to be this. Just that, just wrap it or turn it. I don't know. So this was the first latch. This latch called SR latch. It is coming from set and R reset. Set, reset, latch. Any question about this? Okay, but let's see. I need to clean this too. So this is the clean version of SR latch. So SR latch, as you can see, if R is 1, is first of all, it's just 2 input, R and S. So if R and S are 2 input, they can be maybe. So in this case, it's going to be 0, 0, for example. If S and R 0, so what's going to happen in this case? If it's 0, here is Q and Q bar. So if you OR 0 with anything, that's going to pass. So it means whatever is inside is going to stay. So it's going to be memory. This is the first state of latch. Latch has a state, different states. One of the states is memory. So if inputs, that's why these inputs are control inputs. With these inputs, we are controlling the state of this latch. Is this memory now? Is it set? Is it reset? Or invalid? We have one invalid state as well. So if 0 and 0 is memory, why? Because or This is NOR, but this is OR and NOT. Doesn't matter. This is safe. If you OR anything with 0, anything, for example, Q bar is going to pass because 0 is not affecting in OR. So, and Q going to stay out. So Q was something that was inside, and right now it stayed inside. So it means it's act as in. That's the reason. And if what? Yeah, and I said Q. It means Q can be 0 or 1, whatever it was. So let's see now. What about 0, 1? If it's 0, 1, what's going to happen? If R is 1 and set is 0.
It's gonna reset the value inside.
Yes, it's going to reset. Why? Because if you like OR and NOT, and this is 1, whatever is Q is going to make it 1. Don't care about the Q. And after passing this, it's going to be 0. So it's going to change to 0. That's why we call that reset. When the reset is 1, it's going to get reset. Hey, that's good. So there is control. So we can put something inside memory. And what about this state? Exactly. Like in this state, it's going to be set. So we already created set, reset, and memory. Awesome. So we have everything we want. What about 1, 1? Oh, that's a problem. If there is 1, 1, system not a state. So that's why 1, 1 is not allowed. So it's an invalid state. So we have 4 states. Reset, and invalid. This is how we work with memory for elements. We have different states for memory. Okay? So we got what's going on. So output are complementary of each other all the time. Supposed to be, because we know that it can make them stable. And if we need those outputs, easily they are in hand, we can use them. So Q and Q bar are whatever is inside. Actually, yeah. So the last can be as a memory element. So, and you can have Q and Q bar as an output latch. For example, this is desktop latch. And input R and S. And there is no clock. There's no clock. Okay, so that's good. Let's see what else we can say. Yes, when both inputs are inactive, the latch is memory. So as I explained, and if R is 1 is reset, if it's S is 1, set, and if it's both 1, it's not allowed. But we have 2 types of latch. We have active high and active low, that instead of using NOR, we can use NAND. NAND is more popular. NAND is more popular in systems, especially in like CMOS, CTL, logics. They use NAND instead of NAND is like that. If you use NAND, you need to negate inputs. To negate inputs, is going to be similar to no. Anyway, NAND and NOR can be used to make latch. So we just going to have active high latch or active low latch. So that's the model of active low latch. In active low latch, you have NAND instead of NOR, and instead of S and R and S, you have S bar and R bar. The rest is the same. So we mostly use this as a general memory element, memory latch, at least for SR, because it is with NAND. That has more advantage, but one of them is it's common and also is better. So it's normally NAND is better. Okay, so this was type of latches. So let's go deeper in SR latch. As I explained, set gonna force the output Q1, and reset gonna force the output 0. That's the diagram or circuit of that. And the table is here. We already explained this table. When set and reset are 0, Q and Q bar retain previous state, whatever state was, is stay in that state, and it's acts as a memory. If set is 1 and reset is 0, it actually becomes reset. Becomes set, actually becomes set, sorry, becomes set if Q is 1, and if it's R is 1 and S is 0, Q is 0 and Q1 is 1, reset the state. It's called the state of reset. And if it's both 1, these two are both 0, and it's not possible to have Q and Q are both 0 because they are negate of each other. Yes?
Would the active low be the opposite of that?
No, the active load is just changing this part. That part is the same. In active load, we're going to see that next slide, but in active load, if this is 1, 1, is act as a memory. In this part of the check, yes. It's very similar, not okay. We're going to see active low now. This is active low. In active low, as you mentioned, when you have 1, 1, it acts as a memory. And when it is 0, 0, it's not allowed or invalid for it. And when it's S bar is 0, is set, and when R bar is 0, is reset. Okay, so let's do example. This is example like similar to this. I'm gonna ask a lot. Like I'm saying, okay, S and R like this, give me Q or Q bar. Mostly just one of them. You need to draw it or tell me the, if it's you need to know, for example, 0, 1, and so on. So pay attention to see how I try to find Q. We're asking what is the waveform that will be observed on Q, but we need to assume the value of Q at the beginning. Here, the Q is 0 at the beginning. So the Q is 0. So what we're going to do, we're going to detect states. Okay, here is 1, 1. So this is S bar, R bar latch. Okay, so 1, 1 is memory. 0, 1 is set. 1, 0 is left. 0 invalid. That's important. So we know this. Now we are checking this. Okay, maybe another color. Here, 1, 1. So is memory here. Here is set. Okay, if it's memory, whatever it was is a state. So that's why here we have set. So it's gonna get set. And in this time, 1, 1 is memory. And then 1, 0 means reset. Here we have reset. And here, memory, stay reset. Here is set. Here memory, stay set. Here is set. Memory, because 1, 1 is memory. Here, 1, 0. Sorry, what happened? Oh, okay. Here is 1, 0. So it means reset is already reset. And here 1, 1 memory. And here 0, 1 set and memory. And then here again 0, 1 set. The 0, 1 is set, it stays set. And memory. That's it. Good. Okay, so the cleaner version is this. So you need to be able to compute this. This is the output of the filter. Latch. So that's important. Do you want to do one example? Another example by yourself? Okay, what about you do this? This is S bar and R bar. And Q is 1. You find the Q that was at the beginning 1, and we have S and R. Do it in paper. You can do it together with your friends.
Goes down.
Those things coming to your mind when you do this by yourself. First, you need to see which part is set, which part is reset, which part is memory. So I think we don't have memory. We don't have memory. This is set. Okay. And this is reset. This reset. No memory. Right? So I already, this is the main part. Finding which step, a state is set, which state is reset, and which state is memory. We don't have memory here because memory was actually 1, 1, and we don't have 1, 1 at the same time. So I can solve that by myself, but probably you got the proper answer as well. So it was 1, and it becomes set means one already won, so it's set, and then reset, and then reset. So this is the out. It was one, and then it stay one because we still set it again, and then reset and it stays for that. Still this time, we don't know later. So you got the point, yes? Any question about this? Okay, good. So we did one example. This was race conditions. Yeah, race condition coming to the top. So normally race condition is, if we want to define race condition, we need to have two input for a system. And these two input change together. However, like happening two things at the same time is like ideologically, it's an ideal thing. It's not happening, or maybe we say possibility of happening these two at the same time is hard. So yeah, we can't say two things happening at the same time 100%. Just can say a possibility of happening these two at the same time is very, very close to one. So if this happens, if the system, in this system, two input change together, still this is not race condition. The race condition is when the output depends on these two inputs. So let me write it down. So the race condition is when we have two inputs for the system and output depends on which signal change first. Which signal change first? So this is called race condition. This is definition of race condition. You have two input or multiple input, it's not necessarily two, and they are happening at the same time. They are changing at the same time, but we have some outputs that are waiting to get these inputs changed. They change, and they are kind of relating those changes. So using redundancy for this kind of race condition, okay. Using redundancy that I explained at the beginning of the class, can solve this problem. Because kind of you are forcing the system have another way to be correct, you know. Actually, this also called the system that are fault tolerance. This is another way of designing system to be fault tolerance. Fault tolerance means if faults happen, the system not get failure, not shut down. It's trying to tolerate. One of the methods is using redundancy. So the redundancy here can act as a that bridge to not system get a wrong answer. Okay, so that's the definition of race condition. So what, how this happen in set reset latch or active low set reset latch? It can happen in different ways. One of them is when these two get low at the same time. Because being low is invalid. but at the same time, suddenly, based off the different situation in the circuit, they might get 0 because there is no control in other parts. We can put control, we can see that in the next slide, but this can happen if we don't have control or we don't have a clock, not just clock, edge of the clock to synchronize the system. Later on, we can see we can solve all of this problem with just adding clock. Okay, so that's the race condition happening in these cases. Both S and R, but negate of S and R because it's actually low, get low at the same time. So another one, the latch feedback signal changed too quickly. This is another one. Or that cause oscillating actually the output. You can see that. And another thing, when propagation delay in one gate is a little differs from the other. So this propagation, one of the methods of solving hazard is actually working with this propagation time. This is another general method for solving that, to see if there is a propagation time. And if you think the propagation time might be not similar, we can put some extra, for example, elements in the circuit to make this propagation time equal. This happens when you have more than 2 layers. Like, for example, you have one layer here, and here you don't have another layer, for example. So you can add, I don't know, a kind of gate is just make delay in this level to make this propagation time at the same time. It's just example, but this is some method that exists.
You can just add like double.
If you make double, I was thinking like that, but I think there is.
Even if you only both.
Yes.
To an and or
Exactly. Design the circuit kind of that you have like a level, proper level. If you design the system like that, you can. You want to have levels, and when you design gates, try to make those gates to have the same propagation time. That's possible. So this is one useful general method as well. Okay, this is what happening. If, first of all, this is similar to a NAND. This is similar to this because of the Morgan law, remember? I don't know if this book says this, but they are same. So it means they are active low latch. SR active low latch. And if simultaneously both get low, this happens. Both get low, this starts getting high and low very fast. And system is not safe. There is no other control to fix it, you know. That's why we need another control part, like enable, disable, if you don't want to use clock. Still, we are resisting, don't use clock. But clock gonna save your life later. But we want to see, can we just fix it without clock? Yes, we can, but it still is not the permanent work. Clock is something that we need. Okay, so this is race condition that happening. But how we can fix that? We can put control, enable control. Put one layer, like a control layer. And in this control layer, we would first of all, this active low become active high. This is is for our bar latch, but the general become SR latch. That's very nice, isn't it? Just adding this control, change this to that. Still, we are using similar gates. So this is NAND2. Different shape. I don't know why. Anyway, this is NAND2. And when enable is 1, system working normal. Then enable is 0, a system act as a memory. Okay. So let's check how this can solve the problem of actually raise condition. So you can say, because we have control, we can control it, not we as a human, the circuit can control it. Circuit can control this enable anytime it wants. So adding a control, this control part is a combinational circuit, but can solve the problem of latch, at least for this kind of latch. Okay, so I mentioned two things. First of all, using this control, going to change active low latch to active high latch. I want to ask you why. Because this is not just an and, it's NAND. It's making NOT here too. So X supposed to be S bar, and after passing this going to be S. First of all, this enable is act as a gate. Remember, and is a gate. It enable let S pass. It is 0, always 0. If enable is 1, S can pass. But we put another NOT here to change SR as far as R bar back to S bar. Okay. So you got that. So let's do this example. So this helps solve the problem because is can change when the designer needs it. That's why we can fix this problem. So this is the example. In this example, SR, so it means 0, 0 is memory. R0 is reset. And 1, 0 is set. And 1, 1 invalid. So here we have enable is 0. So whatever was there, and 0 was there before as well. So Q stay, whatever was. Here we make decision. Here we make decision. So it's set. So we make it set. And stay. Here we make reset and stay. Here we make decision, set, and stay. So we made decision based off enable, but that's why this is level control latch. It's not edge control or edge trigger. Okay, any question? Okay, that was just a start. So next class, oh, this is your next class, we're going to talk more about other latches, and our next class, we don't have this. Next, we're going to talk about the latch. So this Friday, we don't have quiz, and we have just a brief class questions. Okay.